Alright, so today we're going to talk about Chapter 8.6, the strong force, the forces that exist inside the nucleus. Okay, before we start this, hopefully you've already watched Rutherford's gold foil experiment on study.com. Okay, that's going to give you essential background about atoms, how they're shaped, and how we know the content of an atom. Okay, so the gold foil experiment here, GFE, gold foil experiment, provided evidence that atoms have a dense nucleus at their center. Okay, so this is our model of an atom, what we typically use to model an atom. This model has two positively charged protons. Okay, it doesn't always have to be two, but it's definitely got protons, and then neutral, zero charged neutrons. Okay, and then our electrons, these little dots here, exist in orbitals around the nucleus. Okay, they exist around the outside. So the nucleus is this little bit here, has positively charged protons and neutral or zero charged neutrons. So NEU, neutrons, are neutral. Okay, all of the particles that live in the nucleus of an atom are called baryons. So baryon is kind of a blanket term that we use to describe anything that lives in the nucleus. So that just happens to be our protons and our neutrons. Okay, so baryons are protons and neutrons. So the exact number of protons in an atom tells us the identity of that atom. Okay, hopefully this is review. So for example, an atom with 6 protons is going to be carbon. An atom with 7 protons is going to be nitrogen. And an atom with 8 protons is going to be oxygen. Okay, so if we take a carbon atom and we add another proton to the nucleus, it's no longer carbon, now it's nitrogen. Okay, once we no longer have 6, once we've added one more, we have 7 protons, now it's nitrogen. Okay? But the number of neutrons in an atom tells us the mass, not necessarily anything about the atom's identity. Neutrons only tell us the mass, or how much material the atom is made of. Okay? Hopefully this looks somewhat similar. If we have a giant C for carbon, okay, we have our boxes. So in this top box here, this is where our mass number goes. In our other top box here, that's where our charge goes, if there's a charge on our atom. Down here, bottom left, the atomic number, and the atomic number also tells us the number of protons. And then down here, bottom right, this tells us how many atoms we have. Okay, how many carbon atoms do we have? So for example, this bottom number here, H2O, that's our chemical symbol for water. H2O, 2 tells us that we have 2 hydrogen and 1 oxygen. Okay, so that 2 down in this box, 2. This here doesn't give us any information about the charge, the mass, or the number of protons. Okay, those are all blank, so we don't have that information. But this, if we have this, carbon with 12, 6, and 0, this box up here, that's our mass box. So carbon with a 12 up here says we have a mass of 12. Carbon with a 6, okay, 6 protons in carbon. Protons are abbreviated P+. And a 0 up here means we have no charge. So neutrons, and hopefully this is review too, the number of neutrons we have is our mass number minus our number of protons. Okay, neutrons equals mass minus the number of protons. So in this case, we have a mass of 12. We have 6 protons. 12 minus 6 means we have 6 neutrons. Okay, so how do so many particles fit inside such a tiny atom? The answer is forces. Okay, forces hold everything together. And we've already defined force as a push or a pull. So forces hold everything together. So the push or pull between charged particles, and our charged particles in our nucleus are protons and electrons. The push or pull between charged particles is called a Coulomb force. Okay, the Coulomb force acts on any particle with a charge. So in our atoms, in our atomic model, the only atoms, or the only particles with a charge, are protons and electrons. So the Coulomb force works on protons and electrons. Okay, we go on to the next page. So the Coulomb force is a force, so it's a push or pull. The Coulomb force happens to push like charges away from each other. So positive, positive, they're going to be pushed away. Negative, negative are also going to push away. Okay, positive, positive would be 2 protons. Negative, negative would be like 2 electrons. Okay, so positive, positive, they're going to push away. Negative, negative, they're going to push away. But the Coulomb force also pulls opposite charges towards each other. Okay, so if you had a proton and an electron, they would pull towards each other. Positive, negative, those are attractive. The other thing we need to know about the Coulomb force is that it gets stronger the closer the particles get to each other. Okay, so the closer you try and push 2 positive charges, the more they're going to want to burst apart. The closer you pull a positive and a negative, the more they're going to want to smack together. Okay, the closer they get, the stronger the force is. Okay, and notice neutrons aren't in this equation because the Coulomb force doesn't work on neutrons. So the real question here is, how do so many positively charged protons live together in the nucleus? How does the nucleus not just explode? Right? They're all positive charge. In our carbon example, we had 6 positive charges in that nucleus. Ideally, they would be shooting out in 10 different directions. So how does that hold together? Okay, the answer is that there's a very strong, very short range force holding everything together. Okay, they called that the strong force, or the strong nuclear force. Okay, they were very creative. The strong force is stronger than the Coulomb force, right? Because it can overcome that want to run away, to part. Okay, the strong force is stronger than the Coulomb force, but it has to be very short range. Okay, if it weren't very short range, all of the atoms would clump together, right? The strong force of one atom would attract another atom and everything would be stuck together. But we know that's not true because in the gold foil experiment, we saw that atoms are mostly empty space. Okay, so we know that this strong force must be very short range. So we can make a chart depicting how all the particles are affected by each of these forces. Okay, so our subatomic particles are protons, neutrons, and electrons. Protons use the symbol P+ because it's proton with a positive charge. Okay, there's our positive charge. Neutrons, N0, because they're neutrons N with no charge, 0 charge. And electrons are E- because electrons E, and minus for the charge, minus charge. Okay? The Coulomb force is going to affect protons because protons have a positive charge, so they will be affected by the Coulomb force. Coulomb force only affects things with charge. Neutrons have no charge, so it makes sense that they're not going to be affected by the Coulomb force. Okay? No charge, no Coulomb force. Electrons, E-, will be affected by the Coulomb force because they have a negative charge. Negative charge, Coulomb force. Okay, and then we talked today about the strong nuclear force. So we have protons, P+. The strong nuclear force only affects things that live in the nucleus. So protons, they live in the nucleus, so they're going to be affected by that strong nuclear force. Neutrons also live in the nucleus, so they're also going to be affected by that strong nuclear force. And then electrons orbit around the outside, so they're not going to be affected by that strong nuclear force. Okay? So hopefully this was pretty straightforward. I have 5 quick questions for you guys to answer. Use these notes to answer those questions. And when you're done, turn it into the bin, and we'll go over the other forces that are responsible for atoms tomorrow.